I took out this rotor and I'm going to change the angle of the magnets. Right now they're kind of flat on, I call it. The face of the magnet, let's say it's actually a 1" by 1/2" disc magnet in there, N52. So that's the way they are now, just the full face facing outward, and it's going north, south, north, south, north, south. Okay. And I have these little screws that hold them in these little epoxy plugs so I can rotate them. So that's what I'm checking out, is different angles to these. So like I did have a 35, I had 2 magnets in there, only 2, some last tests, and I had them slanted like this, 35-degree angle. Now what I'm going to do is, I didn't notice much difference with 35 with the 2 magnets. And what I'm going to do now is have the magnets like this, spinning around like this. So what would you call that? 45-degree angle, I guess. If this is, I don't know what you call it, but it's going to be like here, like this. The next test I do. And this might be similar to spinning some magnets inside a toroidal coil. You see generators like that, it's supposed to be pretty much no lens. When you spin some magnets face on against a toroidal, spinning inside the toroid with a core, a ring core. So I don't know how that's going to be, so I'm going to check it out. Here's what the rotor is spinning against. A 3-phase AC motor, laminates. And this is the original rotor that was in there. And so it was and is an AC induction motor. But now it's going to be what I call a permanent magnet RV, which is short for PMRV. Rotoverter is short for rotoverter. PM is permanent magnet. So what this was, so I can keep track, is a PMRV north-south, north-south. No angle. My last tests. I didn't film my last tests with it like this configuration, but I wrote it all down. And maybe the reason I didn't film was because I was getting a lot of bearing clatter on one bearing insert, I call it, because the original bearings are that size and I put in this size, so I made these inserts. You can see the insert back there. That insert's still good, but this one got chewed up, so I have to make another one. I think I'm going to use Delrin this time, not Teflon. That was Teflon. Delrin's a little more stronger. So here's the tests I did. I call this motor the rotor prime mover. And this is the motor I've been testing a lot. It only draws like 50 to 30 milliamps at idle with no load. It's got ceramic bearings. It spins really good. This is kind of my main test motor. So I'm using this as a pony motor to drive this PMRV permanent magnet rotiverter. And remember, it's a 3-phase AC motor chassis, stators. So I use this to spin this up to speed, which should be about 1750 RPM, and then the AC from the grid, 60 hertz, 120 volts, will latch up with the rotor. And now you have an AC motor working over here, but you have to get it up to speed. I can't use like a start cap like with this one and get it up to speed and then insert the run cap and tune it. Can't do that with this and these permanent magnets, at least not yet. I don't think it's gonna be possible, but maybe it will. It's not that important because I can use a pony motor to get it up to speed and then run it on AC, so it'll be going the AC sine wave latch speed. So here's the tests. Okay, PMRV north-south, north-south. That's this with no angle to the magnets. And I just tested one phase of the 3 phases of this. So I just put the meters across like here, or here, or here, but just one phase I'm testing. 1750 RPM. I made 47.4 volts AC, no load, of course. So that's the maximum voltage I got. No caps anywhere, just seeing what comes out. And 1.37 amps AC, and that's just having an ammeter shorting out this phase. Just an ammeter in AC, and you just put it across here, and it's like a short. And when I test for lens, that's all I'm doing is I will short out one of these phases and then see what happens with the prime mover if the draw goes up. And before, when I had 2 magnets at 180, not 4 magnets, but 2 magnets at 180. In the videos before, it was going up to 110 milliamps from 50 milliamps running this. So it's like about doubling the draw in watts. At 50 milliamps at 120 volts, it's like 6 watts. And then it goes up a little above 12 watts when I short out this over here. So the shafts are connected, so I'm spinning this motor with this motor. This motor, I see what the draw is to see what the lens braking action is from this motor when I short it. So it goes up 50 to 110, okay? This was before with these, with just 2 magnets. And I had those slanted at 35 degrees. You can go back a video, one of my boring videos. Go back and see that if interested. So that's what I get out of one phase at 1750 with this rotor. And again, there's no slant. They're just, magnets are just face on outwards. 1/2 inch by 1 inch round disc magnets, grade N52, about the strongest you can get. And I'll put this in here just to show you the air gap I have between the laminates and the magnets. You can see the face of the magnet's quite a bit back. I'd say about, I don't know, 20 millimeters, 3/4 inch. Quite a bit back because these are super strong magnets. Now, okay, so that's the first test. I wanted to see what I get out of it, and actually it's about double the volts and double the amps as when I had only 2 magnets in there. Now, let's go to this one. Now, the prime mover, the 1/3 horsepower prime mover, this, while spinning the PMRV with 4 magnets, north, south, no angle. Okay, that's what I just tested that I didn't film. I had this in there. What happens is the drag that having these 4 magnets spinning past these steel laminates makes it so this motor now cannot handle it. It can't spin it. It stalls. And so to cure that, I put an 8 UF run cap there. Instead of a 4 UF, I knocked the run cap up to 8 UF. And now I have a lot of draw, 330 milliamps at 120 volts. So you're looking at, I don't know, 36, 40 watts input compared to 6 or 12. And then when I short out one of these phases, as this motor is spinning this motor, now the draw goes up to 450 milliamps, but it keeps going. That's how, when you want more shaft power from a rotoverter, you up the run cap UF. So with a shorted out phase, it's now drawing 450 milliamps compared to no shorted out phase, just spinning it, and it's 330. Interesting. So I went up to 10 UF run cap. Now there's quite a bit of power from that shaft. However, it's 500 milliamps at idle. That means no load. Just only the load is the shaft load of spinning this without it loaded. And now at 500 milliamps at idle, that's around 60 watts. It's a lot of watts for this stuff. And what's interesting is now when I short it, the draw only goes up not so much, 40 milliamps from 500 with a shorted out phase over here. So I only tried out 2 different run caps, 3 different. I tried this one, stalled, and this one and this one. So that's what I got. There will be a perfect run cap that will get best performance, and I could also be stepping down the voltage maybe to 80 volts AC or something, lower the draw. Also, I could be putting an AC cap in series from the power supply and improve performance, but I'm just checking things out. Mainly what I'm doing now, if anybody's wondering what the heck am I doing, I'm checking out the angle of these magnets that spin around inside there. And I can change them easily and then lock them in place with this brass screw. So, like I said, the next one I'm going to have the magnets straight up and down like this. Here's how they are now. I'm going to have them like this, extreme angle. Maybe this will imitate a toroidal permanent magnet generator. Maybe not. I don't know. Okay, so one more kind of boredom. The run cap performance. You know, when I did those loopers, that's what I did, is I just took the run cap, aka rotary transformer phase, and I pull it out with a series transformer, step it down, and tune it with caps a little bit, and shove it into a battery or super cap. It's running an inverter, and the inverter runs it, and I got a loop right there. Pretty simple. Okay, here's the run cap performance. So what I did is I connected them both to the same power supply. So I have 120 volts powering this with a 4 UF run cap now in this experiment. 4 UF run cap into the prime mover rotoverter, just a standard rotoverter, no permanent magnets. Call it the prime mover. And I also powered this, but now with a 39 UF run cap. 39, because that had the best performance of output of the run cap. So I'm treating that run cap like a generator phase, you could call it, or an alternator phase. And what it makes is VARS, V-A-R-S. It's not going to make power unless you load it. But just to see what's happening, you want to know what the VARS is. And so in the prime mover, while it's being powered and spinning this, I had 161 volts AC and 220 milliamps circulating. That's this motor over here. And the VARS of the PMRV north-south, north-south, no angle, that's this motor with this rotor, had a lot more amps circulating, but less voltage. So the VARS of the PMRV was 105.2 volts amp AC and 1.54 amps, while it receives 220 volts AC 60 hertz, and this receives 120 volts AC 60 hertz at the same time. So what's coming right from the grid to power both motors is 1.33 amps AC from grid. That's 120 volts. I didn't write it down, but the prime mover has a 4 UF run cap. This one had a 39 UF run cap. So there's what I got, my last test I did. And you don't have to listen to it run. Just hear my voice and what I wrote down to see So the next test might be something good. If I have these magnets like this, I'll bet you the lens reaction will be very minimal, and maybe there will be lots of power still made. I don't know. So that's what's coming up. I guess that's it. Thanks for watching.